In this experiment, we are going to study hydraulic jump. This maybe is the most interesting phenomenon in open channel flow. You may see it in your daily life, but not recognize it. In your kitchen sink, open the faucet, you can see that the water comes down and touches the surface to create a circle pattern. The water flow inside the circle has a higher velocity than the outside. You may also notice that the depth of water is shallower inside. The circle, the interface, is actually a hydraulic jump. The mechanism of hydraulic jump is often used in many hydraulic structures such as canals, irrigation gates, reservoir dams to tame the high velocity flow. What causes hydraulic jump to happen? A hydraulic jump occurs when a supercritical flow meets a subcritical flow. Assume a flow. The upstream is in a supercritical state with a high velocity, a low water depth, and a flow number larger than 1. And the downstream is in a subcritical state with a low velocity, high water level, and a flow number less than 1. When they meet, a transition must occur to reduce the upstream velocity and to raise the water level. This transition between two states must experience a region of rapidly varying flow, where the ebbs and flows cause turbulence that can reduce or dissipate a proportion of the kinetic energy. With the decreasing of the velocity and the increasing of the water depth, the water in the previous supercritical flow merge into the subcritical flow. Hydraulic jump can often be observed when the radial gate of a reservoir opens to release the extra volume of water. Radial gate is often used in many hydraulic structures to regulate the water level. It can hold the water to a certain level, and when the water level gets too high, it can open the gate up to reduce the water level. Due to the highly pressurized state, the water come out from the gate is usually in a supercritical state. And when a certain downstream condition is met, the hydraulic jump will occur. The experiment we are going to do is to use the radial gate in the experimental flume to create hydraulic jumps. You can adjust the setting of the flow rate, the radial gate opening, the height of the downstream weir to find some correct condition for hydraulic jumps to occur. Let's talk about the radial gate. The radial gate can hold the water level H0 in the upstream and push the water through the opening. The pressure still accelerates the flow even it leaves the opening. You can see a region of contraction where the water depth becomes shallower as the velocity of the flow still increases. Later, the contracted flow will meet the downstream flow to create a hydraulic jump. In the experiment, we take the depth of the contraction as the water level before the hydraulic jump. Although the hydraulic jump can dissipate energy, the conservation of momentum of the flow before and after the jump can still hold. The ideal condition of hydraulic jump can be described as Belanger momentum equation. In this equation, the ratio of y2 to y1 is a function of Fr1, where y1 is the water level before the jump and y2 is the predicted water level after the jump. Y2 is also called conjugate depth. Fr1 is the flow number of the flow before the jump, equal to y1 divided by the square root of gy1. This condition can be used to predict the downstream water level given the velocity and the water level before the hydraulic jump. If we know y1 and v1, we can first calculate the flow number Fr1 and substitute into the Belanger equation to get the predicted value of y2. However, this equation has several assumptions. First, the velocity is uniformly distributed over the cross-section. Second, the pressure condition is hydrostatic. Third, the boundary share is ignored. These assumptions are not realistic in the experiment, so that the predicted Y2 may be different from the real measurement. What if the condition in Belanger equation does not meet? Let's use Y2 to represent the predicted downstream depth using Belanger equation, and YD is the actual downstream depth. In scenario A, where the predicted depth Y2 equals exactly downstream depth YD, the hydraulic jump will occur right after the contraction region. In scenario B, where Y2 is much higher than the downstream depth YD, the hydraulic jump cannot occur because there is no water to jump. Instead, the flow after the contraction will pass through a gradually varying region to increase the water level to Y1 prime, so that the predicted Y2 prime can match YD. In this case, the hydraulic jump moves away from the gate. Next, in scenario C, where the predicted Y2 is less than YD, the hydraulic jump will still occur but gets submerged by the downstream flow. To make meaningful measurement, we need to avoid this submerged situation. There are different types of hydraulic jump. You can use the Froude number before the jump to classify them. If your Froude number is from 1 to 1.7, which is not far from the critical state, you will see an angular jump. In this case, you may not be able to see an abrupt transition, but only a slightly ruffled water surface. If your Froude number is from 1.7 to 2.5, you will see a weak jump. In this case, you can see eddies and rolls on the water surface. If your Froude number is from 2.5 to 4.5, you will see an oscillating jump. This jump is not stable, oscillating from the bottom to top and creating waves beyond the jump. Next, we will have a stable jump if the Froude number ranges from 4.5 to 9. This is the most desirable type of hydraulic jump, as it has a good energy dissipation and a large rise in water level. The location of this jump is also not sensitive to the downstream depth. Finally, if we have Froude number greater than 9, we will have a strong jump. The turbulence and energy dissipation is too large, and this type of jump can be dangerous. One of the major functions of the hydraulic jump is energy dissipator. To quantify the energy dissipation ratio, we use the specific energy as E equal to H plus V squared divided by 2G. For a given location, such as before the radial gate, the specific energy E naught equal to H naught plus V naught squared divided by 2G, and so do E1 and E2. The energy dissipation ratio of the radial gate can be found as 1 minus E1 divided by E naught. A similar equation can be found for the energy dissipation ratio of the hydraulic jump. First, turn on the experimental flume and set a flow rate. You can try any flow rate you want, and 60 could be a good start. Once you finish setting the flow rate, you can push the start button. Before you do anything, you need to wait until the flow reaches a stable state. What I mean stable is that the current flow rate has reached your target flow rate, and the water level in the flume does not change. But you may not see a hydraulic jump at this time. The next step is to adjust the height of the radial gate opening. You need first to lose the grip and adjust it up and down to set the right height of the radial gate. Then you can fix the grip by tying the screw. Next, you go to the hand wheel near the outlet of the flume to adjust the height of the tile wheel. The tile wheel is located inside the outlet. You can raise it up or lower it down to control the height of the downstream. This is not very precise, and you need to try a little bit. When you raise the tile wheel, the hydraulic jump may occur and move towards the radial gate. At this moment, you want to adjust the weir so that the location of the hydraulic jump becomes stable. You also want the jump to be as close as possible to the gate, since the height of contraction will be better representative to the water level before the jump. You also want to avoid raising the downstream level too high. That could submerge the hydraulic jump. Once you succeed, you can start taking measurements. You need to write down the upstream water level H0, the height of radial gate opening A, the water level of contraction H1, and the downstream water level H2. Now, you can change the experimental setting, such as the flow rate, radial gate heights, to find a different hydraulic jump. Here is an example on how to analyze the data. Given Q equal to 60 cubic meter per hour, H1 equal to 4 cm, and B, the width of the flume, equal to 30.9 cm. Ask what is the predict downstream depth H2 after hydraulic jump, and what is the calculated energy dissipation ratio. First, we need to calculate the V1 for a rectangular cross-section region. V1 equal to Q divided by A and equal to Q divided by H1 multiplied by B. We know the value of this factor, and we can easily get the value of V1 as 1.35 meter per second. Next, we can use it to calculate the flow number, FR1. The equation of FR1 equal to V1 divided by the square root of H1 multiplied by G. We know V1 equal to 1.35 and H1 equal to 0.04, and we get a flow number FR1 equal to 2.18. Then we can use the Belanger equation to get the ratio H2 to H1 equal to 1/2 multiplied by the square root of 1 plus A FR1 squared minus 1. We know the value of FR1, then we can get the ratio between H2 to H1 as 2.62. Because we know H1 and we know H2 equal to 2.62 multiplied by H1, that's equal to 0.105. We can use the same cross-section formula to calculate the velocity V2 as 0.51 meters per second. Now we are ready to calculate the specific energy before and after the jump. According to the equation, E equal to H plus V squared divided by 2G, we can get E1 equal to 0.133 meter and E2 equal to 0.118 meter. Finally, we can calculate the energy dissipation ratio of the hydraulic jump, R equal to 1 minus E2 divided by E1. The result is 0.150.